Welcome. The next idea that we are going to discuss is about the concept of correlation. So, here, when we have two random variables, the covariance of these two random variables are defined as expectation of x minus mu x and y minus mu y, where this mu x and mu y are the expectation of x and y respectively. So, this is how we define the covariance between these two variables. So, when we just take when we just multiply them and using the properties of expectation, we get to see that expectation of xy is covariance of xy is expectation of xy minus mu x mu y. Okay, and here there are some notes to be remarked. If they are independent, then the covariance would be 0, because when they are independent, this expectation of xy can be written as expectation of x multiplied with expectation of y, that becomes mu x product with mu y, therefore it becomes 0. Okay, and remember, the converse need not be true in general. That is, if the covariance is 0, it does not necessarily imply that x and y are independent. Okay, covariance of x comma x is simply variance of x, right? So it is expectation of x square minus expectation of x the whole square. So that is the variance of x. And variance of x plus y would split into variance of x plus variance of y plus twice the covariance of x comma y. And when the random variables are independent, we will have variance of x plus y is same as theta variance of x plus variance of y. These are some straightforward implications from the covariance expression. Okay, when we have two random variables, there is a chance that one may depend on the other or the other may depend on one. How much they are depending on the one another, that measure we call it as correlation. Okay, it can be either positive or negative. So when it is either positive or negative, it indicates what, like if it is positive, that would be the case when one increases, the other also increases. Okay, in the negative case, if one increases, the other should decrease. That is the case of getting the correlation to be negative. Okay, here in this video we are primarily interested in Carl Pearson's correlation coefficient, and that is denoted as rho, and the expression to find out that one as covariance of x comma y upon sigma x sigma y, and sigma x sigma y are the standard deviations of the variables x and y, right? Here there are some notes to be noted again. If x and y are independent, what would happen? The covariance is 0, isn't it? If the covariance is 0, uh, of course the numerator becomes 0, therefore rho is 0. Okay, and note that this correlation coefficient should lie between -1 and 1. Indication of rho to be equal to either -1 or +1 means the expression, the dependence is linear. Okay, and rho square is the measure for the percentage of linear relationship between the variables. Okay, how much. And we might have seen in our usual probability theory that this some rho is appearing in the density of a bivariate normal variables, right? So this rho appearing here is the correlation coefficient between those things, like between those two variables that we are interested in. Okay, so it is like finding the covariance is some straightforward question, so that is not the thing that we are interested in this video. We are interested in the inference concerning rho. So once we have a bivariate data, actually from bivariate population, the sample correlation coefficient is given by r equals sxy upon under root sxx product with syy. So what are these sxy, xxs and syy? These are the usual notations that we have seen in the regression theory. Okay, so we just calculate all those values from the bivariate data and substitute in this formula to get the value of r. Okay, if we assume the population is bivariate normal, Then we define the z statistics to be like this. With, if this is the z statistic, of course this should have some mean and variance, right? That mean is given in terms of row, and variance is given in terms of the number of data that we have taken. Okay, so here the hypothesis would be what? So like, it is a z statistic. Okay, not standard normal one, it is simply a normal one. So if we have to standardize it, what do? We just subtract uh, z with mean and divide it by the variance, right? So that is how we get some standard normal statistic. With this only we will test the, we will make the hypothesis testing. Okay, if you are testing for the significance of correlation coefficient, we will let rho to be equal to 0. So that would be the null hypothesis. Here we have a bivariate data. Okay, we are asked to calculate r and test the significance at 1% level of 1%. Okay, so with the usual sense we calculate these three values. Once they are calculated, we just substitute them in the r and we find out r value. Now that we have found r value, next we'll have to test it, right? So for testing, what do? We substitute all these values into this. Okay, here when we are about to test for the significance, if we are testing for the significance, test for the significance of correlation coefficient, yes. Okay, here we have found r to be equal to some value. So I can, if that is the coefficient or not, that is what we are going to test against the hypothesis that that is not, right? So we just substitute, excuse me, test for the significance of correlation coefficient, right? Significant. Okay, so in that case we let rho to be equal to 0. Actually here some typos there. Here we'll have to let rho to be equal to 0 against this. Okay, so we just substitute the r value into it, and we do the remaining calculation and we get z to be equal to this one. And for this level of significance, we read the value from the table, and we just compare z and z alpha upon 2. It is in the rejection region, so we reject the null hypothesis that it is not significance. Okay, here a problem states that n is 25, r is some value, and we are asked to test the null hypothesis again some alternate hypothesis. So directly information to test the hypothesis is given. So we just substitute these values into the standard normal statistic and we calculate that value. Okay, it is one tailed, so we will check the condition accordingly, and this led us to accept the null hypothesis, right? Okay, so basically whenever we have a hypothesis testing, of course some confidence interval can be found. So here the confidence interval for this correlation coefficient is found using this. So all you have to do is that, come back to this. Okay, we will calculate z alpha from the table. Okay, so whenever we have absolute of z is smaller than z alpha or z alpha upon 2, if it is one tiled, it would be z alpha. This absolute of z, we may have plus and minus, that one we'll have to calculate accordingly. Okay, so if it is going above this, then that is the case where we reject it. Okay, so absolute of z less than z alpha upon 2 is the region of acceptance. So from that we can very well deduce this one. So it is just a matter of doing some simple calculations. If you do it, you will get the confidence interval from this. Okay, here we have a problem which which represents some bivariate data. We are asked to calculate r and the confidence interval for rho. So in order to calculate r, what do? We calculate sxx, sxy and syy, and substitute in the formula to get calculate the R value. Once it is calculated, we will calculate the Z statistic and the table value. Okay, and we just substitute it in the this one. We just substitute in this one and see, this is the confidence interval for row. I think there is some typo in it. You can check the calculations by yourself, right? So, and this is a slight idea or some remark that we'll have to make. Okay, till now, through the same ideologies, like by calculating all these three quantities, we were dealing with regression as well as correlation, right? So we may have a doubt or a question in our mind that do we have any relation between them? Yes, of course, we have a relation between them. Okay, so consider x and y are two random variables and a bivariate data is given. So the regression line is of this form. Okay, so here we calculate b and a in terms of these three quantities s x x, s s x y, and s y y. So this one we take it as b1. Okay, so when we take this as b1, we will have a regression line, that is writing y in terms of x would look like this. Okay, so it is just a matter of, like, usually we write as y equals a plus bx. So we just substitute the values of this is our b1 and this is our a, right? So when we just subtract it from the mean and do some calculation, this is how we get something. Okay, in a similar way, uh, we do some other calculation, that is again the regression line of y on x. Sorry, actually it is x on y. There is again a typo here. The regression line of x on y would look like this. Okay, here we calculate the value and here we will write something of this form. So now this b1 and b2 are the regression coefficients. So when you product them, it is same as that of your r square. So r was what? R was correlation coefficient and b1 and b2 were the regression coefficient. We can very well establish a relation between regression coefficient and correlation coefficient. So this tells us that they are related to one another. Okay, there is a relation between regression coefficient and correlation coefficient. So that's it. Thank you.